So looking at the little diagram here, looks like most everything's a base. Sorry, most everything's an acid. A lot more acids than bases that are around us, right? Food flavorings, a lot of things have very acidic properties. A lot of vitamins, almost all of them have acidic properties. What's kind of interesting, though, is more often than not, when these guys do their job, and like an acid, it turns into a base. When the base does its job, it turns into an acid. It's very often times. And we're going to call those conjugates, but you'll see that in a little bit. But you can't get away from acids and bases. They are everywhere. I thought this was kind of interesting. These guys who figure out this stuff in the first place could just as well live on another planet. I mean, this guy taught himself to read at the age of 3, right? Arrhenius. And then he goes to, he must have enjoyed science, and he goes on and tries to get a degree, right? And in these European countries, I guess at the time, they give you grades. You don't just pass or fail. Oh, you're now Dr. Arrhenius. No, they actually give you grades and helps you get a job, or not, I guess. Well, he got a D. Doesn't sound very good. But man, the guy won a Nobel. So who's right? All right, so anyway, so that's how things go. Don't stick to what you believe, right? So if you had lab yesterday, you found out that ammonia is actually a base, NH3, and you know it's kind of weird because usually when you think of base, you think of what? Not NH3. You think of what for base? OH, and for acids, you're supposed to think of H pluses. So anyway, let's see how this is working here. So there's three ways of looking at an acid and a base, but if you always just remember acid, think of it as H plus, and always think of base as OH minus, you can really get your way through all these 3 definitions, and you'll be okay. Right? For example, Arrhenius. What did he say? He said when an acid is placed in water, right, according to his definition, Israel, it's going to produce a whole lot of what? It's an acid. You put it in water. Solution gets acidic. It's because there's a whole lot of what? What'd you guess? Right? Well, acid should be what? You get a whole lot of H pluses, right? Just think of acid and H pluses. And like I said, that'll get you through a lot of this, right? So if you have an acid, it produces a lot of H pluses. That's what makes it so acidic, because they're so readily available. When a base is put in water, Jalen, according to Arrhenius, you'd have a lot of what? Probably OH, right? OH minus. So I think we've been trained in general chemistry pretty much Arrhenius's way, right? But that doesn't really answer the questions for all types of compounds. And like you see a lot of drawings around the chalkboard here that we're going to be erasing in about 20 minutes as we go up to the boards, but all that nice art. But some compounds, they call them acid-base reactions, and there's no H plus or OH minus. Okay. Instead, you have this guy, Lewis. We've drawn Lewis dot structures, remember? He has a lot to do with electrons. So Lewis, he defined an acid as something that accepts or donates electrons when forming a bond. So Brittany, now they're talking about forming a bond. Oh, do you want to shut that off?
Yeah.
Oh God, there's only one way, and then you got to pull the plug. Ugh. Okay. So I'm picking on, who am I picking on? Jesus. Okay, now think an acid is a species that accepts or donates electrons. So go back to my little guide here. My little guide here is you're supposed to think of this as an acid, right? So that guy could only accept or donate electrons. Well, what charge? I think what charge is an electron? Electrons are everybody. Electrons are negative, right? Well, so he could easily accept an electron, right? And if he's going to donate electrons, he has to get even more positive. So he's going to be an acceptor, right? So an acid is a species that accepts electrons. That's the only way I can remember this. Because I think of an acid as H+. Well, H+ can accept electrons. It's positive. No big deal. Okay, a base. Christina, I'm hoping that you think of base as OH minus. Donates. Has, hydroxide has a negative charge. Something that can donate electrons. It already has excess. OH negative. Okay, that's how I keep them straight. And then we have Bronsted-Lowry. The last definition of acids and bases. Okay, an acid is a species that donates. Oh, who am I picking on? Victoria. Acid is a species that donates what? What'd you guess? Acid, so it has to be H+, right? It's kind of consistent in that sense. If it's an acid, donate H+. If it's an acid, accept electrons. If it's an acid, you make a whole lot of H+ in water. It's hard to see the difference between Arrhenius and Bronsted-Lowry because they're both kicking out all these H+, but we'll see why in a little bit. And then a base would be something that accepts. Marcus, what would you say? It accepts. This one's going to take a little thought, I guess. If it's a base, it would react with what? Well, it would react with. Well, what would react with OH minus? Acids would, right? What would react with H+? Bases would. So that's the kind of thinking here. A base is a species that accepts H+. It'll grab onto it. Okay. So one compound gives them up. Oh, that's the acid. All right. He donates H+ to something else, and a base is something that accepts an H+ from something. Okay. And where this is getting into, and we're going to see this, it's called conjugate acid-base pairs. I'm kind of jumping ahead a little bit, but that's where it's coming from. Oh, that's what the next question was. Let's leave it for that. According to Bronsted-Lowry, blank acid-base pairs differ by the presence of one proton. Conjugate, yeah. Okay. So you have two compounds. All they differ is one H+. They're called conjugate acid-base pairs. Let's see if we can pick some out. Reaction A. Kelly. What two compounds differ only by an H+? And if they differ only by an H+, technically they're a conjugate acid-base pair. You see, can you pick two of them out in reaction A? Well, yeah, okay, you pick a product. Pick this guy. Pick the first one. On the reactant side, I take away an H+, I'll just be left with the F-, right? Notice how you can't just take away an H. You have to take away an H+. So that means you have to have a negative left over, right? Because it has no charge at the beginning. So this would be an example of a conjugate acid-base pair. So all they differ by is an H+. Is there another one up there? Or not? Yeah. The H2O and this funky thing. Because they differ by an H+. If you get H+ to H2O, you get H3O. You have to add the charge, so +1 and 0. It makes it a plus. So these two would also be a conjugate acid-base pair. All right. Here's a question. Okay, so these two are conjugate acid-base pairs, right? HF and F-. Which one is the conjugate acid? Which one, Jacqueline, would be the conjugate acid? Would it be the HF or the F-? The HF. right? It's got an extra H to donate, right? So F minus would be the conjugate base. How about in Monica? B. Pick out a conjugate acid-base pair. Yeah. So once you know what you're looking for, they're not very hard to pick out, right? Which one of those that she picked, Jacqueline, would be the conjugate acid? NH4 plus. Everybody, which one would be the conjugate base? NH3. We've gone full circle. That is a base. By whose definition? Who's the dude who has the conjugates? Bronsted-Lowry. So that the technical jargon would be, when you say, oh yeah, ammonium's a base. Well, if you want to sound really like you know what you're talking about, ooh, NH3 is a Bronsted-Lowry base, right? Because that's the definition. But a base is a base. It doesn't really matter, right? But that's where it's coming from. Are there any more conjugate acid-base pairs? Are the remaining two conjugate acid-base pairs? Do they differ by an H? Yeah, they differ by one H. Well, technically one H plus. So these are also. Okay. So this is the last question, and then we're going to go to the boards and see if we can knock out the rest of this stuff. Actually, H plus is a bare proton, right? Because H is a hydrogen atom, and you look up here on the periodic table, it only has one proton, so it only has how many electrons then? One, right? Well, you rip off that one proton, you don't have H anymore, you have H plus. Sorry, you rip off that one electron, and you don't have H anymore, you have H plus. And they're trying to say that H plus is a bare proton, and it really doesn't exist in water. Instead, you get that H plus, it reacts with water, and you get H3O plus. Now, what's the name of it? Hydronium. Okay. So really, we've been cheating this whole time. Whenever we had a reaction and we had H plus, we're not supposed to write H plus. We're supposed to write hydronium, but it's chemically the same thing, right? You just have to add an H2O to both sides. Okay. So here's some little animations that I found. I don't know if they help you or not, but if you just kind of drag along here, right? They're trying to show that. What are they trying to show here anyway? Oh, he's ripping off an H plus. All right, see how that little yellow ball is getting torn off? Oh, if he really helps. This one might be better. Oh, okay. And here, what are these guys moving around? Water, right? Because you recognize the oxygen and the two H's. Okay, now they're going to bubble in HCl. It has an H out front, so it's a acid. So they bubble in this HCl. Okay, and then notice how you're left with the chlorine and that little H plus floating around. It grabs onto a water, so you really have H3O plus floating around. So the more HCl you bubble in, right? What happened there? Yeah, the more H plus you bubble in, you get more H3O, right? The more HCl you bubble in, you get more chloride anions, but all those H pluses right away get converted to H3O plus. What's this one? So just trying to make more H3O plus. Right? See, you see how they're floating around? A lot of H3O plus floating around. So they're just little animations that try to show that, hey, you know, it's really hydronium and not H plus. But okay. So I say that's good enough. We can knock the rest of the stuff out together. So you can bring your notebook with you if you don't want to be staring up at the screen. And hopefully there's chalk and erasers everywhere. Spread out as much as you can. So you can jump in here. Ugh. Okay. So our first question is to write the balanced reaction of hydroxide ion. Right? look at, jump over here with one thing. He doesn't need all that room. Look at that. He can't even erase it all. Write the balanced reaction of hydroxide ion with hydrofluoric acid, with HF, to form fluoride ion and water, and then identify everything as an acid or a base. So first, identify the reactants, write them on the reactant side, identify the products, put them on the product side, and then we'll identify acids and bases. So see if you can pick them out. Good. Most everybody remembers what hydroxide is, right? OH with a what charge? Negative, right? That's your hydroxide. Keep going. Once you get them, identify the acids and the bases. All right. I think most everyone's got this. There's only one thing wrong with what I wrote. Do you catch it? What am I missing? The F needs a minus on it, right? Because it's fluoride, right? So hopefully you have that. And then write acid or base under each one, right? A hint is if you can identify the conjugate acid-base pairs. Because once you figure out what he is on one side, you know what he has to be on the other side. Yeah, good, Brittany, you got it. All right. Oh, and then this guy, here's another conjugate acid-base pair. Did you get him? Yeah. Yep. I think most everyone agrees, right? Here's a conjugate acid-base pair. Acid and the base. And then hopefully identify the water, right? Another base. But here's its conjugate acid. Right? They differ by an H+. Everybody agree? Okay. Let's try the next one then. Give the conjugate base. So you look at these compounds, they're supposed to be acting as the conjugate acid. So HNO2 is a conjugate acid. This guy is a conjugate acid, this arsenic polyatomic ion. Write down their corresponding conjugate base. What would it be? What would the conjugate base be? What do you have to do to generate it? Take away an H, you're close. H+. Take away an H+, and you'll have it. So you can write a reaction for it, or just write it down. Right? It would have to be what? Yeah, exactly. No, you don't really have to write a reaction if you don't want to. You can, but you don't need to. It would have to be, take away an H or just H+, you're just left with what? Does everybody agree? What do folks have? I hear an NO2. So close. NO2 minus. Right? NO2 would just be removing a H. But you have to remove a charge, too. You have to pull with it. You have to remove a whole positive charge. Well, this guy, right? Whoop. Okay. If you want to write a reaction, that seems like a lot of work, right? you have to write H plus, and then plus whatever's left over. Oh, it would be NO2 minus. All right? So that would be our answer. Do the same thing. Write the conjugate base of, what is that, dihydrogen arsenate or something like that. Write its conjugate base. Rip off an H plus, and you'll have it. You're close. You just got to rip off, take away another.
You take off both?
You got to take away a, no, take off one, but if you take away an H plus, you have to add a negative 1 to whatever the charge was. And originally it was a negative. No, what's a negative and a negative? Negative 2. All right? Now notice in going from HNO2 to NO2 minus, we added a negative 1. We added a negative 1 to the charge, right? Because you get negative 1 plus 0, you get negative 1. What's the charge on D's compound? It's a negative to start out with. Add a negative to it, you end up with a negative and a negative. Negative and negative isn't positive. Negative 2, right? Negative 1 and another negative 1 would be a negative 2. So whatever you write, you need to have a negative 2 on it. Right? Because like up here, we added a negative 1 to the charge to get our answer. Because you have to take away an H plus. So we just add a negative 1. This guy, the negative is kind of written down low. All right? Usually you try to write him up higher. Right? He's a negative charge. So you're going to end up with a negative 2 charge. And then write the compound. Minus 1H. So it'd just be HASO4. Right? Okay. Now do same game, but give the, we're giving conjugate base again. Give the conjugate base to these. Give the conjugate base to these acids. Give the conjugate base to these acids. Take away an H plus.
It's the same. Is it the same way we would do it?
Mm-hmm. Yep.
And that was
You got it.
Okay.
HSEO. So rip off an H plus. Okay, so you got to take this, so he's got to be gone, and add a negative 1 to the charge. So he's gone. So this is just your answer right here. Yeah, that's it. Because a negative 1 is negative 2. But this shouldn't be there. Get rid of him. Right? So this is your conjugate base. Unless you want to write a reaction. Arrow, and then you have H plus this. That works. So did you get SEO with a negative 2? Good. For A, and SEO with a negative 2. Yeah, starts out negative, you got to keep it negative. Good point. You just got to add a negative 1 to it. And HOCl, you'd end up with OCl with a negative 1, because you have to add a negative 1 to it. Right? Right now it's 0. So OCl negative 1. You're always adding a negative. You're always adding a negative. When you're writing the conjugate base, because you have to rip off an H plus. But now we're writing conjugate acid. In this next one, we're writing a conjugate acid. Getting warm, Jesus?
Oh, a little bit.
I'll plug this guy in. There he goes. Now we're writing the conjugate acid. So you have to do what to these conjugate bases? Add an H plus, right? Add an H plus. Add an H plus. So it'd be H plus, H plus this thing. if you want to write a reaction. Minus plus 1. Correct? You have a negative and a plus, but it ends up being 0.
So no minus.
Yeah, just nothing. That's how we write 0. Right? So if you like reactions, you'd write, I guess you'd write this, right? I think it's a lot of work too. Right? But the answer is HClO. Right? How about the B as in boy? See if everyone get a consensus for B as in boy. The next one, that arsenic trihydride. It's conjugate acid. What are you writing for him? Ooh, you're close, Naya. ASH4, but you have to add not just an H, add an H plus. So you have to add a plus 1 now. So it's going to be ASH4, but I have a plus 1 up there, right? Do you see that? You end up with a charge. Does everybody agree? Add an H plus?
But because the CLO minus makes the added one, that
Yeah, you're always adding one.
so then it goes to 0.
Yeah, because it started out with a negative 1. Yeah. If it would have started out with a negative 2, you end up with a negative 1. Okay. How about for the following reactions, label everything as an acid or a base and indicate the conjugates. Label everything as a conjugate acid or conjugate base, and you'll be good. Oh, he's a plus, Desiree. That's a plus. There you go. Mm-hmm. Yeah, conjugate's good. Now, which is which? Which one's the conjugate acid? Which one's the conjugate base? The conjugate acid has to have more H's.
So this is the base then, because it's an H4, but over here it's an H3. Is it?
Well, it says how many H's?
That's 4.
This one has 3. So he has one more H plus. So he has to be the acid. He has more H's. Because the acid has more H's. He has to give them up. So he's the acid. If he gives up an H plus, you get this guy. If this guy grabs onto an H plus, you get this guy. So he's the base, he's the acid.
So the whole thing is a conjugate. Well,
Yeah, they're a conjugate acid-base pair,
Yeah.
but then they want you to identify which is which.
okay, so this is
The conjugate acid, and that one's the conjugate base. Yep. Okay. Did you notice how these guys, if he's a conjugate base, he has to be a conjugate acid because acid reacts with base? All right, got another little trick. See if you can identify the conjugate acid and bases in C. Oh,
Or we're not really ready to pay attention to that.
206. He's giving up H2O6. H2O6. Oh, this, he's grabbing onto an H to make another H2O, so he turns into H2O6, right? It's kind of ugly. I think if you figure out these two, and then then you deduce what those are, right? Do you see how to do this one? I say do these first, right? And then you know what the other guy has to be.
Yeah.
So he has to be the conjugate acid. And he has to be the conjugate base. And then you know that this product, aluminum, has to be the conjugate base. This guy has to be the conjugate acid. Right? And if you look closely at it, he's grabbing another H to make the H2O6. Okay. Last one here. Write the Lewis formulas. Oh man, remember how to do that? Write the Lewis electron dot structures of the reactants and the product, and then we'll see what's acting like a Lewis acid with a Lewis base. Okay? Yeah, so write out the Lewis dot structure for BF3. Remember how you kind of just spread them out? Remember how we did all this? You got to count up all the valence electrons. Kind of, it's starting to look like something like this. Remember this? No? Like boron has 3 valence. Fluorine has 7. Right? So in this one alone,
31.
yeah, it should be 24, right? 3 times 7 plus 3. Right?
Oh, we're talking about for this one.
This guy, the number of valence would be this one. Okay, where did I lose you?
All of it, like.
Okay.
It's so different. Okay, let me just look at it.
Okay, what I did is I'm counting up the valence to put in each one of these. So I'm just doing the, all right? So here I have 3 fluorines, that's where the 3 times 7 is from. And then plus 3, that's with the boron. So that's 24 total. So my Lewis electron dot structure has to have 24 electrons on it. I haven't put them in there, right? But you have to do that. And then the fluorine, he's got 7 valence electrons, but he has a negative charge. You have to add them. So this guy had better have 8. 8 dots around him. And this one needs to have...
Can fluorine be hypervalent? It can, right? Because you can't have that.
Oh, it should work out.
It's 31. 7, 14, 21, 28.
No. It's a negative. It's 32.
Oh, really?
Because it has a BF4 minus. Right?
So that's it?
Okay.
Yeah, no, it's 32.
Okay. So make sure BF3 has 24 electrons, fluoride has 8, your BF4 minus has 32 electrons in them, right? Did you get all those Lewis dot structures drawn? So once you get those drawn, and then we'll take a look and see if we can identify the Lewis acids and Lewis bases. But first, make sure you and everyone around you has the right Lewis dot structures. Otherwise, he's not going to make a whole lot of sense here. All right. Here, let me put in my dots. Maybe that'll help you. I'll make my electrons red. So I got to connect everything. All right. So for example, for the BF3, I've only used how many electrons? 20. 3 times 8, 24. Oh, I have used 24. I'm good then, right? Okay, how about the fluoride? Now I need 8, so you just put in 2, 4, 6, 8. So I've used up all 8 there. All right. So everyone see how I came up with 8 valence electrons? All right, because fluorine alone has 7, but they have to add 1 for the charge. And then now you have to draw the Lewis dot structure for BF4 minus. So that's a boron, 4 fluorines, and add 1 for the charge. You get 32. So connect them all. Each fluorine has 8. So that'll work out. That'll be 32. Okay. Okay, now we're supposed, once we get these Lewis dot structures drawn like this, we're supposed to be able to look at these guys, these 2 reactants. One of them is acting like a Lewis acid, one's acting like a Lewis base. Now, since we drew a whole bunch of dots for electrons, Lewis base, donated electrons or accepted electrons? Lewis base, think of base, think of hydroxide. It's got all these OH minus, has all these extra electrons. Lewis base, he doesn't accept. He's a base, right? He's negative, OH negative, right? Think of hydroxide, OH negative. All he can do is give up electrons. He's already got a negative charge. He can't accept anymore. So Lewis base gives up electrons. So one of these guys, either the fluoride or the BF3, gave up electrons. The other dude accepted them. Can you see what happened? Look at all the electrons around that fluorine, the fluoride. These electrons, boom, went over to the boron and made a bond. Can you see it? Can you see it? All right. Just grab one of these. Grab this one right there. That lone pair jumped right in here, right, to make a bond. See that? So which one donated the electrons? The fluorine, the fluoride technically. So the fluoride is the Lewis base. The BF3 is the Lewis acid because he accepted them. Okay. So Lewis acid and Lewis base. So try the homework. I'll be glad to help you out.